Hello my dear friends, welcome back again to our YouTube channel Invisible Threads. Hope all of you are doing well in this difficult period of time by keeping yourself safe. So in my last video I have discussed on dielectrics and its properties, on the different kind of polarization processes also I have discussed when it is placed in an external electric field. So today we are going to learn one new topic called the capacitors and the capacitance. So without any further delay, let's begin. Our today's topic is capacitors and the capacitance. So we can say that the capacitor is a system of two conductors. You can see there is a two conductors, the two parallel plate conductors, or maybe parallel or maybe not parallel, separated by an insulator having different charges and the potentials in between. Usually we take equal and opposite charges for the two conductors, and the potential difference V is equal to the difference of each individual potentials for the two conductors. A single conductor can also be used as a capacitor by assuming the other end is at the infinite distance. For two conductors we can say that if we charge them with the battery, the net charge of the capacitor is 0. So the net charge will be Q minus Q is equal to 0. So one will be positively charged and the another one will be negatively charged. The electric field in the region between the two capacitors, better to say the conductor, is proportional to the charge at each of the conductor. So we can define a property called the capacitance. So what is this? The capacitance is the ability of a body to store an electric charge. So you can see from the figure, this is the two parallel plate capacitor, and here I connected two plates with the battery. This is the positive pole and this is the negative pole of the battery. So here this plate will get the deficiency of the electron, and this side there will be excess of the electron. So this side will be negatively charged and this side will be positively charged, and the electric field direction will be from the positively charged plate to the negative side plate. So now we can say that the potential difference V is the work done per unit positive charge from one conductor to another. So how much the work done is if I try to bring 1 unit of positive charge from positive plate to negative plate against the direction of the electric field. So we can write that the potential difference between the two plates of the capacitors is proportional to the charge, and the ratio of the charge divided by the potential is a constant one, and that constant is defined as the capacitance. So C is equal to Q by V, where C is the capacitance of the capacitor. It's a property. So we can write that the capacitance is the C, or the capacitance. It depends on the geometrical configuration. We will see in our this later video in this part, configuration like the shape, size and the separation between the two conductors. So the capacitance depends on the geometrical configuration. And if we write that if the potential between the two plates of the capacitors is 1 volt, the potential difference, so the capacitance is equal to the charge of each of the conductor. So we can write that the capacitance of a conductor is defined as the charge required to raise its potential through 1 unit. So if V is equal to 1 unit, V is equal to 1 volt, so the capacitance is equal to the charge for each of the conductor, each of the plate of the capacitor. And the SI unit is the farad for the capacitor. Capacitance is coulomb per volt. So there are different multiples of the farad, like 1 microfarad is equal to 10 to the minus 6 farad, 1 nanofarad is equal to 10 to the minus 9 farad, 1 picofarad is equal to 10 to the minus of 12 farad. So now if we put some dielectric or the insulating material in between the plates of the capacitor, the maximum value of the electric field that the dielectric medium can withstand is called the dielectric strength of the material. So now in between this thing, in between the two parallel plates of the capacitor, if we put some dielectric, so we know, I have already told that in between the two plates there will be that electric field at some specific direction. So if we put some dielectric here, the electric field will penetrate the dielectric and the dielectric will sustain a maximum amount of the electric field. It is called the dielectric strength of the material. So the air is also a dielectric as an insulating material or insulating substance. For air, the dielectric strength, the maximum amount of electric field, the maximum value of the electric field that the air can hold is the dielectric strength. So it is the 3 times 10 to the 6 volt per meter. So we need to keep in mind that to store a large amount of charge without leaking, the capacitance should be high enough such that we don't exceed the potential difference or the electric field limits. So there is a limit to the amount of charge that can be stored on a given capacitor without the significant leaking. So now we will move on to discuss one specific type of capacitor where the conductor plates are parallel to one another, and it is called the parallel plate capacitor. So now you can see that this is the parallel plate capacitor, and here this is the parallel plate separated by a distance of d. On that there is two plate 1 and 2 I marked here. On the plate 1 there is the positive charge distribution and the negative charge distribution is on the plate 2. So the total charge is capital Q and the charge density is sigma for the plate 1, and for the plate 2 the total charge is minus Q and the charge density is minus sigma. So and it is the separation between them is small d. So I will consider the electric field lines, the electric field direction will be from the plate 1, from the plate 2, you can see from the direction. Now you can see that the two plates have the charge plus Q and the minus Q, and the plate area is capital A, separation is small d. The plate 1 has the surface charge density sigma is equal to capital Q over A, charge per unit area, and the plate 2 has minus sigma, like it has the minus Q charge. So we can now write that we will now consider three different regions. You can see from the figure that at the point A, which is top of the plate 1, at the point of B, which is in between the two plates plate 1 and 2, and at the point of C, which is below the plate number 2. So you can see the electric field at any point at the point of A at this point. So what it will be, you can see for the plate 1 the electric field, this is the positive charge, so electric field acting on the point A will be acting upward, and for this negative charge for the plate 2 it will be acting downward, and it is independent. We know that for the infinite plane the electric field is independent of r, is the distance, so it is sigma by twice epsilon naught for the plate 1 and sigma by twice epsilon naught for the plate 2, but it is acting downward. So for the point A, the electric field, the resulting electric field, the magnitude of the electric field is 0. You can consider for the point like for the point of C, similarly for this plate number 1 the electric field is acting in this downward direction, and for the plate number 2 the electric field is acting towards it. So the electric field similarly for the point of C is similarly as 0. The electric field at any point C below the plate is E is equal to sigma by twice epsilon naught minus sigma by twice epsilon naught is equal to 0. Similarly in between the two plates at the point of B, plate 1 and 2 at the point of B, you can see for the plate 1 the electric field, this is the positive charge, so electric field will acting towards point plate 2, and for the plate number 2 the electric field also acting towards it, so the total electric field will be add up. So at the point B, so electric field in the inner region between the plate A1 and 2, what it will be, E is equal to sigma by twice epsilon naught plus sigma by twice epsilon naught is equal to sigma by epsilon naught. I put the value of sigma is equal to Q by A, so it is sigma Q by epsilon naught A. Now we can say that the electric field is localized between the two plates and it is uniform throughout it. Now here we assume that the plates of the capacitor don't have any finite area. So I assume that the plates of the capacitor don't have any finite area, means they are infinitely large. It becomes if they are finite in length, the plate of the capacitor is finite in length, so we need to consider the fringing of the field, means the electric field will not be same at the edges of the plates. So I consider the plates to be at infinitely large. So we can write that we have got in between the region of plate 1 and 2 the electric field will be Q by epsilon naught A. Now for uniform electric field, the potential difference what it will be, V is equal to electric field times the distance between the two plates, it means capital Q D by epsilon naught A. So the capacitance is equal to C is equal to Q over V, capital Q over V is equal to epsilon naught A by D. So this is one important relation for the parallel plate capacitor. The capacitance depends on the area of the capacitor, the area of the parallel plates and the distance between them, and epsilon naught is called the free space permittivity. So as I discussed before that the capacitance depends on the geometrical configuration, you can see for the parallel plate capacitor it depends on the parallel plate area and also the separation between them. So suppose for A is equal to 1 meter square and D is equal to 1 millimeter, we can say that the capacitance is equal to 8.85 times 10 to the minus 9 of farad. So now we will move on to one step ahead. We have already discussed in our previous video that the effect of the dielectrics when it is placed in an external electric field. So we have already seen what happens when we place one dielectric material in an external electric field. So let us see in the presence of a dielectric material how the capacitance gets modified. So we will see the effect of the dielectric material on the capacitance, on the expression of the capacitance. So effect of dielectrics on capacitance. So you can see there is similarly like before, this is a parallel plate capacitor. So 1 and 2, there are two plates which are parallel to one another. In here this is positively charged, plate number 1, and the plate number 2 is negatively charged, and the charge density is sigma and minus sigma. So if I place in between the two parallel plates one dielectric material of thickness d, which is almost equal to the separation between the two plates, so it will get polarized and the dipole moments will get aligned along the direction of the electric field. So you can see this is the direction of the electric field and the dipole moments are aligned along the direction of the electric field. So this side, you can see this side there will be some bound charge. So the bound charge appears only on the surface of the dielectric. So this side will be negatively charged and this side will be positively charged. So here on the plate there is a charge density sigma, and the bound charge that has been developed in this side for the dielectric, because I placed it in the external electric field, I will define it as minus sigma b. You can see it is written here minus sigma b, because it will be negatively, this side of the dielectric will get negatively charged only in the surface, because I have assumed that it is the uniform polarization. I have discussed in my previous video what is uniform polarization, what is non-uniform polarization. So I have chosen that it is uniform polarization. So this side will be negatively charged. So without the absence of the dielectric, I have calculated that the capacitance will be epsilon naught A by D, where epsilon naught is the free space permittivity. Now I put the thickness of the dielectric substance is, I choose like that it is almost equal to the separation between the two plates. So I have already discussed that the bound surface charge density at the surface of the dielectric will be sigma b and minus sigma b. So this side will be minus sigma b and this side will be plus sigma b. Now the electric field in the dielectric will be due to the net charge density. So for the top plate, what it will be, sigma minus sigma b, because it was sigma previously there. Now the induced charge is minus sigma b, so the net charge density will be sigma minus of sigma b. Similarly for the below one, what it will be, sigma b minus sigma. So now the field inside the dielectric, what it will be, E is equal to sigma minus sigma b by epsilon naught. So as we have already discussed, it is sigma by epsilon naught in between the two plates. So again the bound charge density sigma b is proportional to the initially the previous one, the electric field value of the previous one, which makes the dielectric polarized. Sigma b proportional to E naught is proportional to the sigma, the charge density on the plate, on the parallel plates. So we can write that sigma minus sigma b is equal to sigma by k. K is a constant, it depends on the dielectric, and we choose that k is greater than 1. So after replacing the value of sigma minus sigma b, we get that, and we can also define that the V is equal to E times D. So in this side of sigma minus sigma b, we put sigma by k, so the potential becomes sigma d by k epsilon naught. Now we put the value of sigma is equal to q by a, the area, where a is the area of the parallel plates. So it comes out to be qd divided by k epsilon naught a. So the capacitance is C is equal to q by v, it comes out to be epsilon naught k a by d. I define this quantity epsilon naught k as epsilon a by d. So epsilon, I have written here that you can see that I have chosen that epsilon is equal to k times epsilon naught. So now what you can see that if k is equal to epsilon is equal to k times epsilon naught, then k is equal to, we can write it like epsilon by epsilon naught. It is called epsilon r, the dielectric constant of the medium, and epsilon r or k, you can write epsilon r or either k, which is greater than 1. So we can say that the dielectric constant of a substance is a factor by which the capacitance increases if we replace the medium inside of the parallel plates with a dielectric material. So you can see previously it was epsilon naught a by d without the absence of the dielectric, with the absence of the dielectric, but in the presence of the dielectric it is epsilon naught a by d times a factor of k, and k is equal to epsilon by epsilon naught, or we can write it as epsilon r, is called the dielectric constant of the medium. So in the presence of the dielectric material, the capacitance enhances, so it is, and the constant is greater than 1. So it is useful in use, we can use it. So my friends, I am concluding my discussion here. In my next video I will discuss more on capacitor and its different kind of combinations. If you have any kind of problem of understanding, don't hesitate to let me know in this video's comment section. Stay tuned and keep supporting Invisible Threads. Stay safe and thank you.